The title, people may be wondering what about the first three words that came there. So I like to start that out with explaining where that came from. There we go. So that comes from a poem by who I consider the original poet laureate of the North, Robert Service. And it's from the Ballad of the Northern Lights, and if you'll indulge me, I'll try to read this here. They danced and they danced like the devils dance over the naked snow, and soft they rolled like the tide upshoaled with a ceaseless ebb and flow. They rippled green with their wondrous sheen. They fluttered out like a fan. They spread with a blaze of rose-pink rays, never yet seen by man. So that's a really nice introduction to Aurora. And in fact, I can imagine if I'd never seen the Aurora, those words would probably give me at least a sense of what you might expect to see the Aurora. Now, actually, who here has not actually seen the Aurora before? That's what I thought. That's good. So we can sort of dispense with the idea that nobody has seen it before. So that's a very evocative words. But is that really an accurate description of the Aurora? Well, it's accurate in that it evokes what we think it is. And it certainly conveys the excitement and the pleasure of watching the Aurora. And that's certainly been around for a long time. But as technology has advanced and we try to actually quantify what's going on with the Aurora, it's been fun to watch how that technology has advanced and how our understanding has advanced. So here I'm showing over a century of observations of the Aurora. This is a couple of Norwegians, Karl Stormer and Birkeland, in 1910, making observations of the Aurora. This is some of the first work to determine the altitude of the Aurora. And you can see back there, and obviously the way to do it was with lots of furs on, and using a film photograph. Those are plate glasses. They took tens of thousands of plate glasses from two sites, and using triangulation, they were able to determine the altitude of the Aurora, and they were quite accurate. It was pretty amazing for that technology. And then we work up to today. Here's a state-of-the-art imager I'll talk about a little bit later. And here's the kind of hardship I have to go through sitting in my office at Poker Flat. And I'm not wearing as much fur as they are, but it's nice and warm there. And then, so the description of what we can do with all that data, here in the Middle Ages, that's what they could do. They could draw pictures trying to figure out what was going on. And their ideas were candles or ice crystals in the air. And now we can do amazing things with the digital revolution, computational power, visualization. We can do amazing things with that. Now, that's all great, and we still got to ask the question, just because we do that doesn't mean we understand it any better. So basically, advancement of technology, they can enable improved understanding, but not necessarily so. So one of my goals tonight is to make sure that anything I show you is showing you advancements and not just replaying. I don't know how many times I've gone out and made a measurement, and then I'm about to think about publishing, and I go off and look, and somebody's already done it. Somebody back 30 years ago. So a lot of things have been done already, so I want to make sure we're moving ahead. Now, here's a little bit of an outline for the talk. So I want to make sure everybody's on board here. I'm going to do like a 101 of Aurora in about 10 minutes. Now, that's going to be a little hard, but I want to make sure everybody's sort of on the same page, at least as far as what we're talking about as far as the measurements. Now, I'm a bit of a gearhead, so I'm probably going to talk about the technology, the cameras, too much, and not enough about the science. So we'll try to get through that quickly. But I'm going to talk to you a little bit about what we're doing now and how that is different from what was done even 20 or 30 years ago, let alone 100 years ago. And I'll try to talk about the science discoveries that have come out of this amazing advance in the digital technology we see now. So, and I'm going to give you a few words here. Again, for these lectures, I always have to remind myself I'm not sitting at the GI, and if I say some of these words, not everybody knows what they mean. So here are a few things. Photon. Now, for a long time, people thought that light was an electromagnetic wave, and that's true, but it also comes in individual packets. And so we call a photon one of those individual packets, and you can actually go off and measure a single photon. So it's undividable quantum of light. By the way, its energy is inversely proportional to its wavelength. The wavelength is the color you see. Quantum efficiency, I'll talk about that a little bit later on, but basically it's how well a detector measures the light coming into it. We'll talk about that. You'll see a lot of places we're going to put a capital R or a KR. That actually stands for a Rayleigh. That's named after Lord Rayleigh, English physicist from 19th century, I think. Anyway, that's the unit of optical brightness. So a bigger number just means it's a brighter aurora. You don't need to know what it really means. And the last thing is a kilogram. It's a kind of a funny thing that we use a lot. The aurora is actually a 5-dimensional problem. You've got 3 spatial dimensions, you got things there, you got time moving around, and you also have wavelength you got to worry about, the color of the aurora. And I can only display maybe 2.5 dimensions on a screen like this. So we have to make compromises. So one thing we do is what's called a keyogram. So we take a series of images like that, and we take a stripe down the middle, and we just lay it out vertically like that over time. And this is what that looks like. So this is the red part of this image down here, and you can see here about 950. Sure enough, there's a little bright red spot there, and you can see that red spot there. So what you can do is you can tell where in the sky, south to north, the aurora was brightest as you went along. So there'll be a lot of places where I show different kinds of keyograms, and that's what I mean with a keyogram. It's basically just slice the sky and lay it out in time. They used to do this mechanically. They'd actually have a film camera moving along with a slit, and they would just expose it for a little bit of time, move it over, and expose the next time. But we can do that digitally now. Okay, so what causes the light in the aurora? Well, what happens is electrons, those things that spin around the outside of the atoms, they're accelerated somewhere out deeper in space. It's what's called the magnetosphere. We don't need to worry about that right now. They get accelerated to high speeds, and I mean like tens of thousands of kilometers per second, very fast. They come down, and they have to follow magnetic field lines, but they come down toward our atmosphere, and as the atmosphere gets thicker and thicker, we get towards the surface, there are more of these atoms and molecules in the way, and they bump into those. When they bump into those, they lose a little bit of energy, and through a process we'll talk about in a second, what comes out is a photon, a little bit of light. So what we're seeing is the result of electrons bumping into our atmosphere. Now this is the same thing that happens in a neon sign. Now I don't know if everybody's, well, I don't know if physicists maybe spend too much time in bars, but we've been in a lot of bars and seen neon signs. It's the same sort of thing there. Hopefully you don't do that. This also happens between about 100 kilometers and 300 kilometers altitude. That's about 60 to 180 miles. So when you're watching an aurora, the bottom of that aurora is about 60 miles high. So it's a long way above those clouds. Let's see, I can do that. The other interesting thing is, and back in the 19th century, people started doing this. They started taking a lot of spectra of different things, and one thing they did is took a spectrum of the aurora. So if you take some white light, like from the sun, and you bend it through a prism, what you usually get from the sun, you get a rainbow, right? You know, that's what happens with the raindrops in the air. If you take the same, or if you take light from an aurora, you bend it through that same prism, instead of getting this nice sort of smooth transition from color to color, well, you get a whole bunch of individual colors that come out, and sort of gaps in between. So it's kind of interesting. It took a while for them to try to explain that. So why is that the case? Well, if you go back to grade school and talk about how atoms and molecules are made up, right? So the nucleus in the center, and these electrons are orbiting around there. Now I put circular orbits here. It's not really circular orbits, but this is a good schematic. And what happens when an electron comes down, a high energy electron comes along here, bumps into that atom, and the first thing it sees is the electron. It gives that electron a little bit of energy, so it can go from that low energy orbit to a little bit higher energy orbit. So it goes from here, it bumps up to this guy up here. So that's the excitation process. But everything likes to be at the lowest level. You know, you put a marble on a hillside, it wants to roll to the bottom. The same thing happens in the atom. So it wants to go back to its lowest energy state. So it does that, but it has to lose some energy. You can't create energy out of nothing. So when it does that, out comes a little bit of light. And because these orbits are very well defined in energy, when that transition happens, the energy that that photon has is very specific. And because that energy is very specific, the wavelength is very specific, and that's what makes up all those individual lines in the spectrum. Well, this is great because we can actually use this to discern both what species are being excited up there, and it also helps us determine how energetic those particles really are. So I'll give you some hints here, and you can go amaze your friends with saying, oh, well, that's obviously oxygen aurora. So if you see the really deep red up at the top, very high altitude stuff, that's atomic oxygen. Now the oxygen we have right here is mostly molecular oxygen. This is atomic oxygen. It gets split at high altitudes. The green line, and that's what most people see, is a lot of green. That's also atomic oxygen. It's just different sets of states. When you get really good aurora, you see this nice pink lower border like that. That pink lower border is a combination of some red, neutral molecular nitrogen and some sort of blue-violet ionized molecular nitrogen. And that's a sign. When you see those pink lower borders, that's a sign that those electrons are very energetic, or they're coming down deep into the atmosphere where the nitrogen is starting to be more dense than the oxygen is. So you already know a lot of stuff now, right? So if you go and see red aurora, you know it's very low energy electrons coming in. If you see green aurora, that's a good standard one. If you see that pink lower border, those are really energetic electrons. That's all we do. So you guys can be rocket scientists now. Now it turns out if you use the ratios of these, so if you take the ratio of that green and that pink on the bottom, you can actually come up with a diagnostic for how energetic those electrons are. So that's one of the things we do, and I'll talk about that a bit more. I already talked about this, but how high are they? And this gives you an idea of how high they are compared to other things. So here's, as well as I can do in PowerPoint, here's a scale model of the Earth, and here's more or less where the auroras are, right? So Earth is a big place, so that's a long way up, and here's that blown up a bit. Now if we take that 100 kilometers, that's basically the bottom of those arcs. You can see what we can do here. The ozone layer is about 30 kilometers up. Airplanes go to 15 kilometers. Tallest mountain's just under 9 kilometers. Research balloons go up to 50 kilometers. There's some things called noctilucent clouds that are up at 80 kilometers and such like that. So gives you an idea. Auroras are a long way up there. I know they seem kind of close sometimes when they're really active, but believe me, they're basically 2/3 of the way from here to Delta Junction. If you laid them down, or if you drove straight up, it'd take as long. So, and how do we know that now? Well, like I said, Stormer would go out in his fur suit and take pictures from 2 places and figure out they're that high. Now we can just put a camera on a space station and take pictures of it as it goes by. And you can see here's the limb of the Earth out here. That's the edge of the Earth. And you can see the auroras are definitely well above that. And if you measured that, if you could scale it, you would see that those are probably, the peaks of those arcs are probably at 110 kilometers, something like that. Now this kind of points to what I'm going to start talking about now, is just how amazing the technology is now to do this. The first images from, anybody remember Skylab before the space station? The first images from Skylab, the astronauts came up to Alaska to the Geophysical Institute and were trained by a fellow there named Tom Hallinan to take those pictures. So we were involved with some of the first images of aurora from the space station that way. You can go to some NASA sites and get lots of these. I've got a couple of more I think I'm going to show at some point. And one more thing about auroras, people think there are lots of different forms, and that is true, but the way the aurora looks also depends on where you are when you see it. And here's a little bit of a schematic. So here I've got an auroral arc. One thing about these arcs is they do move up and down, or they are lined along magnetic field lines. And those are tilted a little bit here. They're more or less straight up and down because we're so far north. But if I've got a camera here and I'm looking at that arc, it turns out that arc's actually quite thin. In fact, there are cases where we've measured arcs, at least subarcs, as narrow as about 100 meters. Most arcs are about 2 to 4 kilometers wide, something like that. But if I move a camera over here, or I happen to be here when I'm looking at the aurora, now it looks like a drapery. That's just the difference between, sometimes you see the arcs on the horizon, you see them as draperies, but you get this thing called the corona aurora, and it looks a lot different. You can see how thin things are. Okay, so we've learned a little bit of the aurora. Let's think about how we want to image the aurora. So we've got individual emission lines. So it turns out if we use some narrowband filters to image it, that might tell us, especially if we want to do things like look at the ratios of the emission lines. So we want to use filters. I showed some pictures earlier on. You can see they're highly dynamic, and we know that from watching them. When they're really bright, they're moving really fast. So we probably want, and that's both in motion, how they move, and also intensity. Sometimes they're very dim, sometimes they're very bright. So we probably want to use high frame rates. We want to take movies at high frame rates. There's also, there's also a large range of intensities. So we want a camera with large dynamic range. We want lots of levels to be able to measure that. And the other thing we know, or I will tell you, is that we're also usually photon starved. Meaning, even in this room right here, we've got a lot of light coming around. When you go outside to watch the aurora, unless it's a really bright aurora, there's not much light coming out of that. So what we really need is a lot of high sensitivity cameras. And I'm going to tell you how that has improved over the years. So I had this whole plan about telling the whole history of imaging aurora, but I think I'm going to shorten that quite a bit because we need to move on to talk about the science of aurora. But the interesting thing I thought about as I was talking about the imaging technology is that's actually just the opposite of what happens in the aurora itself. So remember back to the aurora here, you've got electrons that come down, they bump into something, and it creates a photon. Well, now I've got a photon I got to deal with. I got to collect that somehow. Well, the way I do that is that photon comes down, it bumps into something and turns into an electron. And because I've got electronics, not photonics, but electronics, I can now do something with that photoelectron to be able to measure it. So, like I said before, a key parameter in the imaging is the efficiency of how this conversion medium that turns that photon into an electron, how efficient that is. And that's called the quantum efficiency. And basically all it is this: if you've got 100 incident photons coming in, if you've only got 10 electrons coming out, then your quantum efficiency is 0.1, you only get 10% of them. Now for imaging the aurora, that's not what we want. If we've got 100 incident photons coming in and we get 100 electrons coming out, that's good. We're measuring every single photon as it comes in. So what we want is a quantum efficiency that's very high. And the closer we can get to 1, the better. All right? So here's sort of a time history of what we've been able to do. Obviously, the first thing we did was our eye, and our eye has a quantum efficiency I can't remember offhand, but it's actually quite amazingly good, but it's still on the order of about 10%. Photographic emulsion, quantum efficiency about 10%. About 1 out of every 10 photons that comes in actually gets converted to something that you can see on the photograph. The next, and photographic emulsion started in the 1880s. I mean, well, actually it was 1860s, because in the Civil War, there were photographs back then. Electron tubes came along later in the 1940s, 1950s. Quantum efficiency of those guys was about 20 to 30%. This is what's called an image orthicon. I was going to show more pictures of data taken with that. Some people in this room spend a lot of time working with image orthicons. It was always quite a treat when the graduate students finally got to be able to touch the image orthicon. The control panel for that thing looked like a nuclear, control panel for a nuclear power station. There are knobs all over the place. Each of these little individual things back here had a knob for it. So it was quite a treat when we were able to finally to be able to touch that and run it. Then we went on to image intensifiers. Again, they're kind of 20 to 30%. By the time you actually get to CCDs, and image intensifiers came around in the 1960s. CCDs came, some of the early CCDs were in the late 70s, but the real ones people started using were in the 1980s. Now we've jumped up to about half. So now we're getting about half of the photons coming in are turning into electrons that we can use. CMOS, this is sort of out of sequence. Those are the newest ones. And they've sort of taken a step back, but there's some advantages there. But really, the gold standard now, if we use a CCD and you process it in a certain way that you basically put it together, turn it over, and then basically take off part of the back, it turns out to be very, very efficient then. We're getting quantum efficiencies now of 90%. That's about the best you can do, right? If you got 1 or 100%, that's it. So this is really the thing that's changed a lot, is we've changed our sensitivity about a factor of 3 to 4 in about a 20-year period. So here's what a state-of-the-art camera looks like. I won't belabor it. So lens up front to image. Here's a filter cell. Like I said, we want to filter things. We want to be able to look at individual lines if we need to. Some relay optics back here, and here's this camera right here. This is about a $100,000 camera, because these cameras, the processing for those chips is very expensive. So this is going to be a little experiment here. So here's an old intensified CCD. So this basically went to a video recorder of some sort. And here's one of the new cameras here. What I'm going to try to do is catch it as it goes by. I've done nothing to these two things, but what you can see is the contrast in this is just a lot better. You've got more dynamic range. You've got a lot better resolution in the whole thing. But it really is a really amazing advance. Now, I didn't talk about the optics themselves, the glass that runs the camera, that focuses stuff. That really hasn't changed much. I mean, the glass has done a pretty good job. The other thing that's really amazing now is obviously everybody knows about computational power. In the 1980s, we had TRS-80s and early IBMs. Now my cell phone has more power than any of those computers did back then. So the ability to do the analysis of all these digital images is all really pulled along too, as well as the speed to be able to collect all the data at the same time. Okay, so I'm just going to run through a sort of a vignette of several things that we've been doing the last, I'd say, about 10 years now, and try to talk about how this advance in technology has helped us do this. Now, one thing that is very key to people who work on the aurora is what's called the auroral substorm. Now, the auroral substorm, for us who like to go out and watch the aurora, that's when the aurora is really dancing around, very active. That happens nominally about every 2 hours when the conditions are right. But the reason that happens is not well known. That's one thing we're still working on. We've sent many missions up there to try to figure this out. It still eludes us for several reasons. This last year, Toshi Nishimura at UCLA has made great strides using a couple of cameras that we've been running here at Poker Flat. Basically what he's showing here is, here's where the substorm happens. That's when the aurora really brightens up and you see all that activity. What he's curious about is what's the activity going on beforehand. And what he sees, here's a keogram, but we really call it an east-westogram. Instead of looking north-south, we're looking east-west. And with that, we can see these waves sort of rolling in. And what he's been able to find is he's got some wave structure that's nobody's really ever been seen before because the cameras have not been sensitive enough. And he's able to now correlate that wave structure to when that substorm happens, when the brightness happens. And that's going to tell us a lot more about what's happening about in the magnetosphere where these substorms are being formed. So basically this filtered low light level capability was the reason we could do this. With the old technology, it was going to be too hard just because the low light level imaging ability down here was going to be very hard. So here are the images that went along with that, and we've mapped those out. This guy right here, I'll come back to. We've got a radar out at Poker Flat right now, too, that also gives us the density of the electrons at high altitudes. I'll talk about that in a bit more. Here's a different example. Get this started. This is a different night, but it gives you an idea. Again, this talks about the dynamic range of these cameras. So here it is. In just a second, you'll see up here, this guy will bead up and it'll get very bright. Here it goes. And then this is what we call a substorm. What happens is, that's north. These arcs go to the south and they brighten and everything moves to the north and it gets very active. Now this is a time lapse. You can see the time going by there. This is sped up about 30 times. You can see how this camera was able to handle that large dynamic range. We had that very dim aurora beforehand, and then we could see that real bright aurora later on. Let's talk about spatial scales. With these new cameras, if you put on a very narrow lens, you can zoom right into very small scales. Here's a scale, again, at 100 kilometers altitude. Here's a scale of what each of these pixels has, or that's the scale of those images. So we'll be able to see things down to a few tens of meters across. This is a filtered image, and it's taking images at 20 seconds. Again, we're looking at these structures moving across here, which are indicating some sort of plasma wave out in the magnetosphere that's forming them. And based on that, we can work with the theoreticians to understand what that plasma wave is, and therefore what's causing this sort of structure there. And again, what's the source of the aurora that happens here. So that's very fine spatial scale. Again, that's down to tens of meters across. So, kind of the size of this room. But you got to remember that the aurora is about 4 kilometers across. So that's from here to the river or something like that. So pretty fine scale. Now, the opposite, what if you want to look at really, really large areas with pretty good resolution as well? Well, how do you do that? You use an array of cameras. So there's a NASA mission called Themis. Don't ask me what the acronym is because I can't remember anymore. But they decided to put in about 20 different all-sky cameras across Canada and Alaska. And now instead of going for the really fancy, expensive cameras, they ended up going with actually fairly cheap cameras. And that's the amazing thing now is with the explosion in consumer products, you can buy a little camera like this, which is what amateur astronomers use, for less than $2,000. Something like about $1,500 or so. A couple of lenses on front, some electronics underneath it, and off you go. So they put in these 20 across here. These circles are basically showing you an all-sky camera field of view at about 100 kilometers where the aurora happens. And then if you put all those together and you get good luck with the clear skies at all those stations and all the cameras are working, here's what you get. So this is time here. You can see as this moves across, this is where the terminator, that's where the sun has gone down. This is a good night, not a lot of activity, and you can see all those cameras are picking up substorms, a whole bunch of different fields of view, and you can see how extensive the aurora is when it's this active, and how activity over here may not be well correlated with that activity over there. And you also see north to south, you see pulsating aurora down here, where you see active arcs up here. This has been a wealth of information for people in the rural community. Lots of really good information has come out of this. Because at the same time, we've got 5 satellites flying around in the magnetosphere, measuring the particles, the electric fields, other parameters out in space that match those. So this is repeating it again. We'll watch it one more time. Yeah, so there's sort of a first substorm that kind of settles down. You watch here again, there will be another substorm a little later on that happens in that place again. There we go, a little bit more there. But it gives you an idea of how extensive aurora is. It happens everywhere. It happens all across the auroral zone. And when it's really active, it's really active. So we've gone from fine scale, a few tens of kilometers, to thousands, tens of thousands of kilometers across. And these all have about 2-kilometer resolution, so that's quite a number of elements to look at. And again, this is enabled by low-cost cameras in this case, and a lot of computing power, and a lot of networking power. High frame rates. This is not particularly high frame rate, but this sort of drove a measurement we wanted to do. I keep forgetting to mention this. Actually, this is these are the PIs of the rocket that's on the rail out of Poker right now. So they've been out of Poker for quite a while. But this is another one of those kiograms. This is, again, north-south. In this case, it's not an all-sky camera. It's a narrow-field camera. And here's a distance along here. So it's, it's about 1 kilometer resolution. And what they do is they're looking at this pulsation patch, and it does what you're